Good evening, folks. My name is Marc Razze from JPL's Office of Communications and Education, and it's my absolute pleasure to be your host for tonight's edition of the Von Karman series. Tonight, we'll be talking about an exciting upcoming mission called the Europa Clipper. But before we get to that, let me introduce our co-host tonight, also from the Office of Common Ed, my coworker, friend, and just amazing person, Miss Nikki Wyrick. Nikki, hi. Thanks for joining us tonight, my friend.
Of course, thanks for having me. Hi, Mark, and hello to everyone tuning in. Remember, this is your space program, and we want you to be involved with the conversation. So if you're watching on YouTube, X, Facebook Live, or LinkedIn, please ask questions in the chat box, and our social media team will bring in as many as they can during our talk tonight. If you don't see the chat box, please reload, and it should be right there. And I'm so excited to bring all of your questions to this wonderful discussion this evening.
Thank you very much, Miss Nikki. So, Europa, that shiny little moon that belongs to Jupiter, has been an object of scientific interest for a very long time. Its icy crust likely hides a deep, liquid, saltwater ocean with far more water than is even here on Earth. And most scientists believe that the ingredients and conditions necessary to support life are there too. Now, the Europa Clipper mission won't be the first mission to look at said moon, but it will be the first entirely dedicated to helping us better understand this intriguing member of our solar system family and its potential for hosting, a potentially habitable environment. So joining us for our discussion tonight are two members of the Clipper team, Dr. Alberto Cangahuala, the mission system manager, and Dr. Kate Kraft, the project staff scientist, and assistant science systems engineer. I stumble on that every time. Pardon me, you guys. Hello, my friends. Thank you both so much for joining us tonight.
Good evening. Great to be here.
Yeah, very excited to be here. Thank you.
We are grateful for your time, my friends. So, Kate, we're going to start with you tonight. Before we start, though, with any of this Clipper business, shall we say, if you'd be so kind, tell us a little bit about yourself and how you got here.
Sure. So if we could bring up the first slide. I just, for fun, I thought I'd start with middle school me there in the bottom left. I was really into soccer, but I was also just all about space. Like I just cut out the newspaper clippings and, every time there was an article in the paper. But so my dream really was to be an astronaut someday. And but I kind of had a windy path to getting to where I am. And so, if you go to the next slide, I started off by thinking, I really like science and math. I was interested in engineering, so I went to school and studied aerospace engineering. Next slide. While I was there, I got my pilot's license, which is because I loved flying and everything about that as well. Next step, please. And then I got my dream job. I got to go and work at NASA for a while doing engineering. But while I was there, I got to work on some projects with the scientists, and I just was really, really curious about why they wanted us to design these things. And I got to work on the Curiosity sample cup that was going to bring in samples and look for signs of life. And so next step, please. So I decided to go back and study science and learn more about the potential for life in other worlds. And I started out by studying hydrothermal systems on our seafloor, where we actually think maybe life started here on Earth. And while I was studying, the next step, please, I had a little family along the way while I was working on my PhD. And next step, please. And then I got this fantastic job at the Johns Hopkins Applied Physics Lab, where I'm a planetary scientist now, and I get to work on the Europa Clipper mission, where we're going to go and explore for a potentially habitable environment. So I've continued to try to be an astronaut too. I haven't quite didn't quite make it to that goal, but next step, I'm excited to be part of this really fantastic mission as a staff scientist and systems science engineer. I also stumble a little bit on that, but yeah, really excited to be part of the mission.
That's excellent. So thank you so much for sharing that. That's really, really cool, actually. So let's start with Europa itself. I know I mentioned a couple things about it in the intro, but really, let's just start from the top. Why Europa?
Right. So Europa is just such an amazing world. It's really not that big. It's about the size of our moon. If you want to go to the next slide. It's pretty small. It's one of the 4 Galilean satellites that you can see there at Jupiter. Ice covered, fairly interesting surface. And the Galileo spacecraft went and explored there and told us a lot about the moon, and we're hoping to learn a lot more with Clipper. And the next slide, please. So, from the outside, the moon, you see a lot of ice. We do see lots of really interesting features, though, that tell us that this world is pretty active. We see lots of ridged plains and cracks all over the surface. We see these jumbled up materials that we call the chaos material, the chaos regions. We see some craters. We don't see a lot, which actually tells us that the surface has been resurfaced in the recent geologic past. And we also see little dots on the surface that we affectionately call freckles of the surface of Europa. These little features that some are divots and some are raised surface regions, which could be indicative of cryovolcanic activity that's made its way to the surface. So it's a really interesting world. But when you look at the surface of Europa, we think there's an ocean beneath, but how do we know that when we just look at the surface and we see there's ice everywhere? So the next slide, please. What Galileo mission was able to tell us is that when it flew by, so Europa is pretty small, it doesn't have its own magnetic field, but when the Galileo mission flew by, it detected an induced magnetic field at Europa. And what this was happening was that Jupiter's really strong magnetic field was passing through and being conducted through by some material. But because Europa is small and probably doesn't have this liquid iron portion of its iron core like we do on Earth, we think it's this salt water ocean beneath the surface that's conducting that magnetic field through. And so that's what really has indicated to us that Europa has this ocean. So the next slide, please. If you could go to the next slide. Yeah, great. So with this water, and even though Europa is really small, the amount of water that Europa has with this 120-ish kilometer region of ice and water is so much water that if you took all the surface water on the surface of the Earth and you compared the amounts of water, Europa would have almost 2 times as much water as Earth does on its surface. And so this is just so exciting for us to think about the amount, wherever we look for life on the Earth and wherever we find life, there's water. And so this just tells us that there's this really potentially habitable environment there. And so the next slide, please. So the way that Europa is able to keep its water, so it's really far right from the sun. And so the way that Europa is able to keep its water liquid in the liquid form is that as Europa goes around Jupiter, it's flexing. And sometimes it's a little closer to Jupiter, sometimes it's further away. And so this flexing is inducing heat on the interior. So you can see that in the bottom right where you're getting that reddish color there. So in the interior, it's happening in the crust, and it's also happening in the ice shell, a little bit in the ice shell, but it's able to keep that liquid water, that water liquid. And so it's also another thing that it can do with that heat is induce activity at the seafloor. So if you go to the next slide. So that activity that might be active at the seafloor could be like the activity that we see on our seafloor here on Earth. And what's really exciting is that when we explored the seafloor and found these hydrothermal vents at the seafloor that are putting all this chemistry into the ocean there, we found life down there. Now, this is life that's living only off the chemistry at the seafloor. It's not able to get energy from the sun. And so we think that Europa could have a very similar type of activity at its seafloor.
Wow.
Next slide, please.
So there's got to be a ton of scientific interest in this, right? Overall speaking, how do you wrangle all that to define mission goals for something this complex?
Yeah, so it's so much, right? There's all these things that we want to explore about Europa and find more about, and how do we wrangle, like you said, all that together to try to determine, is Europa a habitable environment? And so for Europa Clipper, we've broken this down into 3 main science goals. To explore and characterize the ice shell and ocean, better understand the composition. We see these reddish materials, what is that? Is that stuff from the ocean or stuff from the outside? We want to understand the geology. What's the geology telling us about how the materials might be going in between the surface and the subsurface? And we're also thinking forward to future potential missions for reconnaissance and maybe landing on the surface where we can dig into the ice and look for signs of life. And also trying to understand, is Europa active today? We've seen potential for some of the measurements from the Hubble Space Telescope, and as JWST becomes doing more observations, we're hoping to see more with that as well, and try to get a better understanding of how active Europa is. Okay, next slide. So the way Europa Clipper is going to go about this is that we have 10 fantastic investigations, 5 in situ and 5 remote sensing investigations that are going to look at all wavelength ranges, telling us about what we see with our cameras. We're going to taste the dust that might be getting kicked up off the surface and learn more about the composition of that material through our SUDA instrument and our mass specs. We're going to measure the plasma environment and better understand the interactions of the magnetic field with our magnetometer. And we're also going to do gravity radioscience measurements, which will tell us about the interior. And then we have things like an ice penetrating radar, which will be able to look into the ice shell and tell us about the structure, looking for thermal signatures where things might be active. And then also we have Europa UVS, which is a UV spectrograph, and the IR spectrometer, which will tell us about the composition. And I mentioned the cameras. And so we just have this fantastic suite of instruments that are all going to do all kinds of amazing observations. And then with the next slide, all of these investigations have this really interesting hardware that we've been working really hard to produce and that are being integrated onto the spacecraft. And these are just a few cameos of the instrumentation that you can see there. And the next slide, please. It's just, behind all this is really just all the amazing people, right, that work on this mission. And so I just wanted to highlight and show a fun picture from our team meeting where we always have our guest of honor in the middle there. The monolith is kind of a theme for us to keep things fun and moving along with all this fantastic work from the scientists and the engineers that make this mission possible.
This is going to be a super exciting ride. No doubt you're thrilled about this.
A lot of fun.
Right, so cool. So let's bring Al back then for a minute. Al, hello. Thanks for joining us again. So welcome back to the room. Let me first, before we jump in, let me do the same thing I did with Kate. And if you would be so kind, tell us a little bit about yourself.
Sure. I have a wife and kids, and we live in Claremont, California. If you could go to the next slide, and have a picture of them. And my kids are college age now, and I was teasing them that they might get extra credit if they watch this, but that's okay, kids. I understand if you have homework to do. If you tab again, my interests, my hobbies include soaring. Like Kate, I think the machine and the atmosphere, just how that all works together is just, I think, kind of fulfilling in a way to harness that kind of power to go view, see beautiful vistas and things like that. And I think through hiking too, there's just another way from the ground to see just all these great features that we have on our planet. And I also enjoy doing crossword puzzles with my wife. Solving puzzles is just a fun thing, and boy, work like this just calls for those kinds of skills. So I like to think it's another way to hone those kind of techniques. If you tab again, I just want to say a little bit about how, to the younger people, just a path, Kate and I are sharing our paths, and I'm sure a path that you'd take to come into this business would be your own different path. But when I was a kid, my parents were really great at fostering an interest in space and science in general. And my mom would read me stories about the space missions that were going on at the time when I was really little. And when I was a little older, I remember watching Cosmos on TV with my dad, and we'd be talking about that. And I think a key experience was in high school to go to a governor's school in Pennsylvania, where I grew up. And one of the team projects there was to integrate trajectories to reconstruct the decay of Skylab from Earth orbit, which was still kind of new at the time. That's how old I am. But doing that was really like a key. It was a transformative kind of experience to finally get in the door as to how space works, and to take an example that you could tie to something you had seen in the news really just changed everything. And from there, if you tab again, that led to a PhD and a career in interplanetary navigation before coming on to Europa Clipper. And it's been a great experience to see the objectives of lots of different missions going to other different parts of the solar system. It's been terrifically fulfilling. I can't say enough about it. And so I want to return that to the community. And so if you tab one more time, I have been volunteering with the Pennsylvania Governor's School for the Sciences and with local colleges and high schools, any chance they get like to help build bridges to the younger people and show them what's possible, how they can take their interests and dreams and find a path to make them reality. So I have a lot to be grateful for, and a lot of people help me get to where I am now, and I want to return that where I can.
Oh, that's very kind and noble of you, Al. Thanks for sharing that as well. So, that all being said, of course, now let's go back down those mission lines, go back to the talk, I guess, right?
Sure.
So there are back to what we were saying before, with so many interested parties in a mission of this like scope, how do you begin to architect something like this?
That's a great question. If you go to the next slide, I'd like to pick up where Kate left off. She had mentioned the Galileo flyby. So let's pick up things like in the late 1990s. This is an era where we've had, NASA has had competed missions, and this is an era where there's been the science community has been active in establishing priorities through the decadal science survey of priorities for solar system exploration. So if in this figure, figure A depicts a small Europa orbiter concept that was being pursued as a Discovery class mission. You could think of this as carrying a few tens of kilograms of a science payload to orbit Europa. Then that grew into a different approach, a different architecture called the Jupiter Icy Moon Orbiter project or concept, which was intended to study all the Galilean moons and the Jupiter system. Concurrently with that was the first decadal survey, which established Europa as kind of the highest non-Mars flagship mission priority. Then following that, there was some regrouping, some other activities were taking place, but out of that came a study between NASA and ESA. It was called the Europa Jupiter System Mission concept that had a Jupiter Europa orbiter flown by NASA and a Ganymede orbiter that was to be flown by ESA. Now the latter eventually became the ESA JUICE mission, which launched in, I think, April of this year. And out of the JEO concept, which was led by Carla Clark, that informed the next step, the next round, which was a set of 3 studies: a Europa orbiter, a Europa multi-flyby mission, and a Europa lander concept. And out of those, the multi-flyby concept matured into what you see denoted in E here. That's really the concept we had at about the brink of getting the announcement of a selection of instruments for this mission. Now, with the evolution of these spacecraft designs, there was continuous work on the science objectives. So the main hypothesis and how it was broken down, as Kate described, came from a lot of work, and some pieces of that had been around for literally 2 decades at least. So that has been maturing too. So these paths are not always straight, but there is like a steady cadence of progress over the decades leading to where we are now. So if you go to the next slide, we show you the wonderful spacecraft design that we have to accommodate these well thought out investigations instruments. And it is designed to accommodate them and the resources, propellant, power, data storage, all that to carry out this multiple flyby mission. The panels here span about 100 feet, the width of, or the long side of a basketball court. The square footage is about this, would cover a well-sized 2-bedroom apartment. It's fairly large. And we'll see later, you can see for yourself how large this is. The panels are probably what stand out the most, and what you'll notice attached to them are the dipoles of the radar antenna, the radar instrument. And then pointing out at about 11 o'clock angle is the magnetometer boom. And then the large disc is the 3-meter high gain antenna. And then in more detail on the bus, there are engines, there are other sensors, and of course many of the other instruments are attached there as well. It's quite a design. A lot of work went into the accommodation to make sure that the instruments could conduct their observations concurrently without interfering with each other. like I said, with enough energy, power, and so resources to get the job done. It's a great work of engineering.
It's a beautiful thing to see here at the lab, that's for sure. So you mentioned the multiple flyby thing. Let's dive into that a little bit. What are the advantages of doing something like a multiple flyby design?
Sure. If you go to the next slide, this leverages off of a concept that's been used for previous outer planet missions, in particular the approach used by the Cassini mission in mapping Titan. If you start the animation on the left-hand side, we'll pick up where Europa Clipper is entering orbit around Jupiter. It enters in a large elliptical orbit, and it uses flybys of the Galilean moons to shape the orbit to the proper size. And you can see the orbit rotates, it changes in shape, and the change in color denotes the cumulative radiation dose that it's taking. What we don't depict here is that Europa's orbit around Jupiter puts it kind of in the middle of a big torus of high energy particles that can damage electronics and could just damage the spacecraft. So we designed a spacecraft to be resilient to a certain dosage plus a safety margin or a design margin factor. And we designed the orbit and the spacecraft together so that the dosage is in line with what the electronics and the engineering of the spacecraft can take. And we designed the flybys to get the pieces of data needed to answer the questions that Kate posed. On the right is a depiction of the typical petal. All the petals are slightly different, but there's certain characteristics that they have. First of all, they're in resonance with Europa's orbit. Europa orbits Jupiter once every 3.5 days. And so we pick flybys on a 4-to-1 or 6-to-1 ratio. So it'll take place every 2 or 3 weeks. And you come in, you go into the radiation environment, collect data, you come out, and outside the radiation environment, you have the opportunity to downlink the data, calibrate the instruments, do other, prepare the spacecraft for the next flyby. And so in that way, you're being really efficient. You're only accruing radiation when you're collecting data, and everything else you can do outside the radiation environment. So you get your most science for your radiation dosage, so to speak. So that's the approach we're using to achieve the objectives of this mission.
So what's a standard issue Europa flyby kind of look like?
Let's take a look at the next slide. Here we have an animation. We're going to ride along with Europa Clipper this is a time lapse, which would span about 2 days. And on the bottom left, you'll see what's highlighted are the instruments turning on and off. And you'll see that instruments are being used, one at a time or 2 or 3 at a time. There'll be just looks at the disk of Europa. There'll be sweeps across the face of Europa. We're also rotating the spacecraft and rotating the solar arrays so that the radar dipoles will be presented to down towards Europa. So there's well choreographed activities that are planned for each flyby, and there's the geometry is taken into consideration, the lighting conditions, the latitudes we'll be looking at. All that goes into determining exactly what the details are for each flyby. So each flyby is kind of tailor-made, but there are certain characteristics that are similar across all of them. Now you can see the array being rotated to get the radar ready, and then all the instruments will be turned on at closest approach, and we'll be collecting tens of gigabits of data, and then the activities will ramp down as we recede from Europa. And then shortly thereafter, we'll start sorting the data out and getting it ready for downlink to Earth. So that's a Europa Clipper flyby.
Wow, that's impressive. Is that correct? Am I correct in stating, I think I'd heard that we're going to get within 16 miles of the surface on some of these passes?
That's correct, yeah. Each flyby sets up the other one. That's one of the, as someone with a navigation background, what really intrigues me is that we get a lot of science from each flyby, but we also get 800 meters per second of change of the orbit. Europa acts like a big propellant depot for us. We change the orbit a lot, and these low flybys are very carefully designed so we get the correct change to the orbit to set up the next flyby. So these are well choreographed flyby sequences.
That's going to be impressive. I can't wait. Um,
And the next slide
go ahead.
shows the ensemble of all those flybys. This is the resulting pattern of coverage that you would get through this orchestration of the flybys. And you get really good coverage of the hemisphere that faces Jupiter and 180 degrees away, the anti-Jovian hemisphere.
That's so neat. I love that graphic. I'm sorry. I gotta stare at that for a minute.
Same here.
So, Kate, let's invite you back in if we can. And if you'd be so kind, talk a little bit about the science payload and how like those particular selected instruments are going to help, do the science, achieve the goals, as it were.
Yeah, if you wanted to bring back the slide that had the I think maybe it was slide 9 that had all the, yes, great. So yeah, just a reminder, everyone, these are the 10 investigations that are going to go along with Clipper, and they were really carefully selected, right, to give us just a broad range of data as we go to Europa and try to really go after this complex question of trying to understand if Europa is habitable. Are there habitable environments within Europa, different sections of Europa? How thick is that ice shell? If the thickness of the ice shell can tell us about how easy the material on the surface can be mixing with material from the subsurface. We know that life likes mixing and likes oxidants and reductants. And so it's really important probably for the habitability of Europa to have the ability to have that mixing. Are there lots of fractures in the subsurface that can allow that mixing also in other ways? Is there convection going on within the ice? All of these instruments will come together with their investigation to tell us about that and the ability for Europa to have this habitable environment. So, and just to point out too, want to mention, these teams are from all across the country. We have as well investigators on the teams who are from other countries, and also, so again, it's like the cross-disciplinariness of the instruments themselves, as well as all of the investigations and the team members who are part of those investigations who will make this science possible, because it really is such a complex question and a challenging question to try to address. But this fantastic mission is really going to get at that question for us.
Who are some of those mysterious partners?
Right. So we have team members who are at universities as well as JPL and APL who have built different portions of the spacecraft. So like APL was really involved with the propulsion and the radio frequency, the communications side of the spacecraft. And then we have European partners who are building the solar arrays. And those are very similar actually with the JUICE mission, the mission that ESA has launched that will also be going and exploring the Jovian satellites. And so, so we have partners just across the country as well as across the world.
It's very cool. It's neat to see a mission like of this scope having so many partners involved. I love it. Al, let me bring you back. Catch us up on the timeline. What's going on with Clipper at the moment?
This is a very exciting time in the mission. Last week we celebrated our year out from launch milestone, and last month we ran a system test of the spacecraft. We were simulating launch, trajectory correction maneuvers, orbit insertion of Jupiter, and flybys of Europa with the instruments, operating the flight hardware and software, and that went very well. That was a very moving moment to see these actions take place and with the team online watching this. So that's very, very exciting. Now we've got a lot coming up. We're going to move Europa Clipper into a test chamber to kind of blast it with the sound to mimic the acoustic environment at launch. And there'll also be tests to check that the spacecraft can stand the vibration and shock that comes from the effects of a rocket flight. And then there'll be electromagnetic compatibility tests. We'll turn on all the electronics to make sure that they can work together as designed. And then we'll be moving the spacecraft to a thermal vacuum chamber to see that it can withstand the conditions, the extreme changes in temperatures that we'll expect in space. And then there's just more system testing. We want to make sure that the spacecraft can respond to faults and enact the corrections needed, that it can notify the ground what's going on, and that we are ready to act on those and provide checks that we know how to respond to what the flight system is telling us. So we'll be checking the whole system, the spacecraft and the people, through these system tests and operations readiness tests in the months to come. So a lot of exciting work ahead.
And I want to mention, because you know this too, we have folks, and if you can bring it up, you guys, we have a live feed from our clean room that you can actually tune into and watch when they're doing assembly and testing and stuff like that. So this is on our JPL YouTube channel, which of course we have, and on the project page on our website, you can find your way to that link as well. So check it out. It's kind of quiet down there tonight.
Yeah.
Folks are working some long shifts, but maybe it's dinner time for a few of them. But I encourage anybody who wants you to keep an eye on this. And it will eventually move out of this room, so y'all know, for some of that testing that Al was talking about. When that does in fact happen, usually the feed will go down, but they usually put up a little banner, so you'll know that it's away doing some vibration testing perhaps, and it will be back at a certain time. So be patient, but kind of cool. It's not often you get to see these things kind of under construction unless you actually come to visit the lab. So this is a neat little way to go. Yeah. So I guess let's start talking like timeline as far as science goes. When do we get there, and sort of when can we start expecting to get the science back?
Yeah. In the earlier animation, we had kind of started with capture at Jupiter. If you go to the next slide, we can show you some details about the interplanetary transfer. I'll just start by saying we'll be launching in October of 2024. There we go. And a few months later, we'll have a Mars gravity assist. And that'll take us into an orbit that's in roughly a 2-to-1 resonance with Earth's orbit. So we'll be coming back to Earth. If we could go back to that. Back to that slide. We'll be flying by the Earth right before Christmas in 2026, and then from there we'll be heading on to Jupiter, and we'll have orbit insertion in April of 2030. So it's about a 5.5-year voyage to Jupiter. We'll be doing calibrations and checking out instruments on the way, making sure that the flight system is ready to do the job when we get there.
Very, very cool. I know I'm excited. I know you guys must be too. So this is going to be awesome when we start getting stuff back. So I think, given the time and such, that's a fairly solid summary of the mission. So I think it's probably a good time for us to jump in, check in with Nikki, check in with social media, the audience out there, and see if we can take a few questions for a little while. So Nikki, how's it going out there, my friend? What are we seeing?
Oh my goodness, people are so engaged, and thank you for all the wonderful questions you've been popping into the chat. I don't even know where to start, so I'm going to jump straight in with Marlene on Facebook, who asks, I hope you find life under that thick layer of Europa ice. Is it possible that marine life could exist under the ice in a place where there's no atmosphere? And does the surface without atmosphere have any influence on maritime life, in this case, on the moon of Europa? Kate, why don't we start with you for this question?
Great. Yes. Such a really, interesting question, right? We do search for habitability, like trying to understand, is an environment habitable based on life as we know it, right? So far, we try to think a little bit about what maybe life might be like in these other extreme environments, but at least we kind of have a decent understanding of how life works here. And so, when we discovered life down deep down at the seafloor on Earth, living off just the chemistry, really, mostly, just that chemistry that's coming out from the seafloor and these hydrothermal vents. This just sparked the, this idea that, it used to be, we think, the habitable zone, this Goldilocks zone, you had to be close enough to the sun to get enough energy to have life. But when we discovered that life was living near these hydrothermal vents, just mostly on the chemistry there, like that really allowed us to imagine that on a world like Europa, that is ice covered, no sunlight, appreciable. I mean, it's already way out at Jupiter, and any light that might be getting trickling down maybe to the very edges of if the ice shell's thin, maybe, but really down at the seafloor, it's got to be living off of chemistry. But it could be, right? If life on Earth is able to do it, then why not at Europa? When we think that high tidal forcing is giving that energy at its seafloor to potentially have activity, hydrothermal vent activity, sure. I mean, it's possible, I think.
Possibilities. I like possibilities. Al, I've got a group of questions for you. Both of them, one of them from Jessica on LinkedIn, who wants to know how long will it take for Europa Clipper to travel to Europa? And Colin on YouTube wants to know, what is it going to do during that long transit to Jupiter?
So the cruise is about 5.5 years. And once we get to Jupiter, it'll be another 15 months before we have our first Europa flyby. We'll be checking out the instruments, as I was mentioning. We'll be doing calibrations, making sure everything's working well. We want to target our flybys of Mars and Earth because they give us propellant in a way. The gravitational flyby changes the orbit in a good way to get us to Jupiter with the right conditions. Once we're at Jupiter and we're using the flybys of all the Galilean moons to tailor the shape of the orbit, those will be great opportunities to do further checkout of the instruments to get ready for the first Europa flyby.
Well, I'm glad you all have a plan for what you're going to do with that time, because it's a good bit of time, but we're excited to see what happens at the end of that 5.5 years. So we've got another great question. This one is from Adelmar on Facebook, who asks, if we haven't dug into Europa, how can we be sure about the amount of water it has, or that there is water? And to follow that up, Hattie on LinkedIn wants to know, how do we know it's salt water?
Great
You
question.
want me to
Kate,
go for
please.
it? Right. I mean, so it is right now. It's like we're pretty sure there's a liquid water ocean, but Clipper is when Europa Clipper gets there, we're going to confirm that 100% for sure. And we have several ways to do that with our just amazing, sort of set of instruments, investigations that we're going to do. And so the magnetometry really is like one of the main key ways of determining that we have this conductive material inside of Europa that's allowing this induced magnetic field from Jupiter to be measured. And so in combination with the magnetometer, we're also taking plasma environment measurements. We're going to actually, those measurements together can kind of, weed out some of the noise from this plasma, this, highly active environment, these particle environment that's at Jupiter, because Jupiter has just a lot of radiation coming out from it. So with that suite of instrumentation and measurements, we can really get after, what is the ocean, not only confirming that it's there, but we can tell some characteristics about it, which also help us with the habitability question. So it's like, well, how conductive is that ocean, which tells us about how the level of salinity. So how much salt, like, is it really highly saline? And then maybe that's, we know life can exist here on Earth in highly saline environments, so that wouldn't rule out life or anything, but we, helps us to get at these questions of like, what really are the environmental conditions there, and how might that inform us about the likelihood that life could be in these environments.
It's great to know we're going to be able to do some cool things and look for this habitability, but kind of a little bit more on the engineering side. And so Al, I'm going to throw this to you. Engineered Army on YouTube asks, would data gathered by a flyby truly be sufficient? Wouldn't an orbiter have conducted greater science?
Well, it comes down to, that's a very good systems engineering question. You have to ask yourself, how much payload can I bring, and how much shielding do I need? And you could make, there were, as I described in this orbiter studies, there's like you could think of as the proportion of shielding to science payload that you can bring. And when you're doing everything in a high radiation environment up close, you're always going to be close to the surface, but the meter's running radiation wise. And so you're going to not be able to bring as many instruments for a given size spacecraft that can fit on a rocket. And that was one of the tough conclusions they had to face. It's like, well, we one way out of it is just to race in and out of the radiation environment. That way we can bring more payload, not have as much shielding, so we can have more investigations to be more conclusive about, check in different ways these habitability hypotheses that Kate has stated. So that's one of the big appeals of the multiple flyby approach. But great question.
So we're going to throw this one back to Kate. George on YouTube says, thanks for that explanation you gave. You said it's possible that life could potentially exist at Europa, but how would the instruments detect it? For example, if there were 1,000 whales swimming around, would you know it?
Oh, wouldn't that be amazing if there were whales in Europa? Maybe a different kind of whale that maybe didn't need to breathe as often. But the instrumentation on Europa Clipper is not designed really, like the goal of Clipper is not to find life. That what we're trying to do is determine the potential for life and the potential for this to be a habitable environment that then a future mission could go back with specialized instrumentation to really try to go after the life discover life question. But we do have certain instruments that, if the levels of life are high enough, if there's plume activity at Europa where there's a direct connection with the ocean water making its way through the ice shell and out into space, that we could, because we're going to fly very close, to the surface, and we do have in situ instrumentation that will be, kind of tasting the environment around Europa and telling us about the composition. And so there is the potential that we could see some inklings, some indications of whether there might be some life signals, signals that we look for in terms of the composition and charges and things that are around. But we won't be unfortunately able to be conclusive about it. And that's like, hopefully what we're going to find, right, is this tantalizing information that will make us just be ready to run right back to Europa with other instrumentation and really get after the detection of life question.
Awesome. I mean, it's good to know what we're doing. Just a little further information on that. Asha on LinkedIn wants to know, is there carbon on Europa, and what kind of chemicals would you expect to see on Europa?
Yes. So there is pretty recent measurements of carbon, and I'm pretty positive it was the JWST, James Webb Space Telescope, that made those observations. And so we do know a little bit, right, about the composition of what's on the surface of Europa from these space-based and some ground-based telescope measurements. And we're actually hoping, now that James Webb is out there making lots of observations, that we'll also be able to make more observations of Europa that will be able to tell us even more about the surface compositions and activity potentially, if we see any activity there. So we do know we can learn a little bit about what's present from these remote observations before Clipper gets there, and hopefully that'll just inform us even more about, give us more data to combine with what Europa Clipper is going to be able to find.
So you mentioned talking about data beforehand and combining this data, and we've actually gotten several questions about this. So Bruce on YouTube wants to know, are we looking at discoveries from Juno for this mission? Then we also have Colin on YouTube wants to know, will JUICE and Europa Clipper work together? And then finally, we've got David on LinkedIn asking, are we ever going to send a submersible in the future to Europa, and would that work with the Clipper mission? So maybe Al, you could talk about how we can integrate this with other missions headed to Europa in the future.
So yeah, I think I'm working with the science community, working with the science team on Clipper. Clearly, they're coordinating with the Juno project. Juno for those who don't know, was launched in 2011 and achieved Jupiter orbit in 2016. It has a large elliptical orbit that has evolved over the years, and that has afforded opportunities to fly close to some of the Galilean moons. And so those are great opportunities to pick up science from the Juno instruments. And that we're all benefiting from that. The JUICE mission and the Europa Clipper mission keep in contact. They share trajectories, and there's discussions and planning about the possibility of coordinated observations. I mean, the nature of the missions, they're both outer planet tours, so they have similar kinds of orbits that they'll have at similar times in the Jupiter system. So it's clear that there's something to discuss and see what opportunities are there. So those discussions are underway, and so we'll see, and we have several years to look at that and refine it. Once we get going, we'll know more about our timing, and we can keep refining that. So yeah, we always want to make sure we are aware of serendipitous opportunities to coordinate observations.
Teams always working together. We love to hear it. So I know we are running short on time, but we've got just a few, well, we've got a ton more great questions, but just a few more to ask for tonight. So I'm going to combine another set together. Edison on Facebook wants to know, how thick is the ice crust of Europa? And Slutz on YouTube asks, if there is an ocean on Europa, how are we going to get through that thick layer of ice with a future mission?
Yeah, so maybe I could jump in a little bit. Al, feel free to add anything on. So we don't know exactly how thick the ice shell of Europa is. We tried to come up with some theories based on the geology or the surface features that we see, and trying to do some modeling and try to theorize about it. But one of the exciting things that we'll be able to do is determine the thickness of the ice shell, and it may not be the same everywhere, in all parts of Europa. So we're also going to try to go after those questions. And yeah, we do though think it's probably at least, several kilometers to tens of kilometers thick. And so it would be pretty challenging for a future mission to actually make its way all the way through the ice shell to get to the ocean. But teams, including one that I'm on as well for just doing research, is we are trying to think about that. So, there's been concepts for landers on the surface that can dig down into the ice and sample for signs of life, as well as what we call cryobots, which may be able to melt their way down through the ice shell and take samples along the way, maybe get to some water pockets if there's water pockets in the ice shell. Do sampling, looking for signs of life, very similar to what we would do on the surface in the near subsurface for a landed mission. But yeah, it's exciting, and we definitely are trying to think forward to those types of missions to try to think about it. But Al, I don't know if you wanted to add anything.
No, look, I think you covered the main points. The technologies are maturing, and Earth provides places where those technologies can be tested out and tried out and matured, so that when we find these interesting places, and I hope that there'll be a good series of candidate approaches that we could study to figure out how best to use for a landed mission or a subsurface mission.
So I've got to ask this question before our final question. Danielle on YouTube wants to know, I've heard there are plumes of water vapor on Europa, like those on Enceladus. Is that so? And if they are there, can we fly through them?
Well, so we were talking about this a little while ago. It was like, I hope everybody knows that, like, we don't know for sure. We've seen like some, so Hubble took some great measurements where we thought we saw evidence of plume activity, but it was kind of on the hairy edge of the measurement capabilities. And so we're still continuing to look with Hubble and with James Webb for any activity. But if we get there, if there is activity while Clipper is there, or in an extended mission even as well, we are getting close enough to the surface that if there's plume activity, we should be able to, even if the plume's not active, like right underneath of us, the material stays around Europa well enough that we should be able to ingest, some of that material and tell ourselves about what that material is composed of, and does that indicate to us it's come from the ocean, or is it material that is more indicative of material we're expecting to be coming from outside? So those are some of the measurements we definitely will be able to make.
All right. Well, since we are running low on time, I've got one last question for both of you. And Al, I'm going to have you take a stab at it first. Kylie on LinkedIn asks, Did you receive a bachelor's in aerospace engineering? I'm getting mine right now, but I haven't chosen what I'd like to get my master's in. What would be your advice on choosing the right master's degree to get a job working for NASA JPL or to do research like this?
Well, Kate and I were talking about this, and there's no single path. Tonight we've given two examples. Talk to people. I think reach out to us. We're happy to continue the conversation. I think that's key. Think about what you're passionate about. Think about the objectives of these missions that we've described. See where there's matches, and if you don't see a match, don't stop. We could keep talking. The skill sets needed to make these missions happen just span so much, and it's not just STEM activities. We have people from so many different backgrounds that help make this possible. But we look forward to having that kind of engagement because we all need to pull together to make these missions happen.
Yeah, I'll just, echo what Al said. Really, it's really, about finding your passion. And so, my path was kind of windy, and reaching out to people. I reached out to people that I had heard of working on missions. I thought missions seemed really cool. And so when I did my aerospace undergrad as well, and tried out different things. And so some of it was like not having a fear of maybe changing direction a little bit, because sometimes you kind of say, okay, I've picked this path. I'm going to go forward and finish it. And so if you find yourself being like, well, I like this, but this other thing is also really interesting, maybe give it a try, like do an internship, reach out to people at JPL and APL or other places, Goddard, other NASA places, and try things out. When you're in school, it's like a really great time to do that, because you can try things for a small period of time and then go back to your classes and kind of see what feels like it fits for you and what gets you excited.
Very cool. Thanks, you guys. Nikki, thank you so much for managing that. Great questions, everybody. Thank you for bringing them in. So before we kind of wrap it up tonight, I want to bring up slide number 19, if you would. Thank you very much, my friends. Al, would you like to talk about this a little bit?
Sure. NASA and the project have worked with the poet laureate of the United States, Ada Limon, who created a poem for our mission. It's a message from a water world, Earth, to that of Europa. And that poem will be placed in a couple ways on the Europa Clipper spacecraft. And you all can add your name along with the poem as well and have it on the spacecraft. So if you go to the URLs, you can see copies of the poem. There's an English version, and there's even been a translation into Spanish. You can read about the poem, how it was created, add your name, learn more about the mission through the Send Your Name to Europa campaign.
Excellent. Thank you so much. So, folks, well, that pretty much is about all the time we've got tonight. So on behalf of myself and Nikki and the rest of the team, everyone here, I want to thank Al, Kate, Nikki, of course, the entire social media team behind the scenes, all of our AV and TV production folks. You guys make all this happen. Thank you. And of course, all of you viewers watching this tonight. We couldn't do this without you. This is your space program, as Nikki mentioned before. So we encourage your involvement. The Message in a Bottle campaign is a great example of that. Poke around our websites. Join us for the adventure on nasa.gov, jpl.nasa.gov. And please don't forget to tune in next month. Actually, we've got a cool show. We're celebrating the 60th anniversary of NASA's Deep Space Network. That's how we communicate with all these spacecraft that are out there. So that should be a really good one next month. Take care. Until then, stay curious, stay kind. Have a wonderful night and a great weekend, everybody. Good night.